This is the third part of Lesson 27 in heat transfer. In Lesson 27, we have been discussing thermal radiation emission from real surfaces. In this part of the lesson, I will present representative property data for real surfaces. By the end of this lesson, you should be able to recall from memory representative values for the spectral hemispherical emissivity of a shiny metal, an electrical non-conductor, and white paint. By extension, you should also be able to know what a representative value is for the spectral hemispherical emissivity of black paint. On with the lesson.
Okay, so I wanted to give you a sense of kind of typical behavior of some very common surfaces that you might see. A shiny metal would be one example. An electrical non-conductor is another example. And white paint. Maybe even contrasted to black paint. So this is just to give you kind of a feel for what the spectral emissivity might look like for a particular surface. Shiny metal will be an example of a conductor. And it's shiny because it hasn't been oxidized, right? Like if you heat metals up, the surface oxidizes and they lose their shine. And then you really have an oxide, which is more like a non-conductor than a conductor on the surface. So shiny metals tend to have a relatively flat spectral emissivity actually compared to some other surfaces. And they tend to not really exceed 0.6, and they never really are less than 0.2. And they tend to just kind of slope down over a really wide range of, like this is maybe 0.4 micrometer up to 20 micrometer, a huge range, right? That's the visible to the long infrared spectrum. So relatively flat, just kind of slowly sloping down from a larger value to a lower value. The non-conductor also has a kind of typical dependence, and there's a difference in the visible and the infrared spectrum. So non-conductors tend to have something that looks like this, where they have a low value in the visible and near infrared. This might be like 3 micrometers. And this could be 0.1 to 0.2. And then they tend to peak somewhere in the long IR. So, you know, maybe somewhere around 10 micrometers, and they get really, really big. They come up to like 0.95. And then they tail off again back to like 0.5 over to the 20 micrometer range. Right? But electrical non-conductors, so think like the plate that you eat off of. When you go to eat at the cafeteria, it's porcelain typically, or that's a non-conductor. It's like a ceramic, and it looks white, right? Unless it's been, you know, made to look fancy with some paint or something. But it looks white, right? And I'll say that it looks white because it has a low emissivity in the visible. Okay, and then white paint. So white paint. White paint typically has a very sharp change in its spectral properties around 1 to 3 micrometers, I'd say. And again, it's kind of like a ceramic. It's typically low emissivities in the visible, and it has much higher emissivities in the infrared spectrum, which is why, Beth, do you have a question? Okay, sorry. Which is why white paint is so commonly applied to the surfaces of anything you want to keep cool in the summertime, right? So black paint, I guess in comparison, I can also put on black paint. Black paint typically just looks like this. We're going to talk about something called Kirchhoff's law in a little bit. Kirchhoff's law says there's a link between the spectral emissivity and the spectral absorptivity, and that link is that they're at the same number. So you can also think about the emissivity as the absorptivity, spectral level. So why does white paint work? White paint has a low absorptivity to the visible spectrum, which is where the vast majority of the energy from sunlight is, right? So white paint tends to reflect sunlight away, but it has a high emissivity in the infrared, which typically is the temperature at which it emits from. So you have a high emission, right, of energy at the temperature that the surface is at, but a high reflection of the incident radiation coming in, and so it keeps things cool. Black paint is different, right? Black paint has a relatively high absorption to the sunlight, and so it just absorbs a bunch of extra energy instead of reflecting it away, and so it heats up. We'll keep unpacking that type of behavior as we move forward in the class, right?